welcome back. So I wanted to make another video about the GRE because I get a lot of comments and questions about that, and I know a lot of you have a lot of anxiety about it, and so if I can help relieve that a little bit, I would definitely like to. So I think I showed before my box of flashcards that I helped use to prepare for the GRE. And I had a couple people ask me for the flashcards. I didn't really want to share them because I just made them for myself. And so I didn't know if they would even be useful for other people, and I didn't want, I don't know, any misleading information or anything like out there accidentally. But it seems kind of silly to have this whole box full of cards that I'm literally probably never going to use again. And I was thinking about them the other day, and I was like, what should I do with them? And then I thought, maybe I should actually share them with people that are interested. So what I'm going to do is make them available online. These are just handwritten, so I can't share these specific ones with everyone. So I will link for those below. And then I thought I would also just make a video and go through the cards in case that helps anyone study, in case you want to, study with, like, have someone quiz you, that type of thing is helpful for you. So I'm going to break this up into subject areas. Let's start with the first category, which is classical mechanics, which is these white note cards here. And again, these are just note cards I made for myself, so I apologize if there are any errors in them or if the way that they are set up don't really make sense and aren't helpful for you. I apologize. So the way I have them set up is I have the hint or the clue that I'm trying to answer on the unlined side, and then I have the answers on the lined side. So I will show you the hint, and then I will tell you what I had down as an answer. All right, so Kepler's second law. This is that planetary orbits sweep out equal areas in equal times. Kepler's laws. I love Kepler's laws. I am a dynamicist, so this deck of cards is very near and dear to my heart. All right, underdamped oscillator. So for this, I wrote down the equation, which is x of t equals a e to the minus beta t times cosine of omega 1 t minus delta, as well as the definition of omega 1, which is the square root of omega 0 squared minus beta squared. And I also wrote a little description of it, which is it's a sinusoid with an exponentially decaying envelope. The Euler-Lagrange equations. This is d dt of the partial derivative of L with respect to q dot equals the partial derivative of L with respect to q for each coordinate q. Power. This is a fun one. Power is the derivative of work with respect to time, or F dot v, force dot velocity. Potential energy function. This is delta U equals the negative derivative from 1 to 2 of F dot ds for a conservative force, where F is the force and ds is the displacement. Work by a constant force. This is equal to Fx times delta x, or F cosine theta delta x. So it's the force in the direction of the motion. Mass swinging on a massless rod. What this was for was I was looking for the frequency here. So the frequency, the angular frequency omega, is equal to the square root of mgr over I, where I is the moment of inertia. Kepler's third law. So if you have t for period and a for semi-major axis, then t equals ka to the 3/2, where k is a constant that is the same for all planets in the system. I probably Google Kepler's third law at least once a week, and I still forget it. Center of mass. So this is the total mass times the position of the center mass is equal to the sum of each individual mass times its position vector. Or that's for discrete masses, or if it's continuous, then it's equal to the integral of RDM. energy of a photon. This is E equals hf, where h is Planck's constant and f is the frequency of the electromagnetic radiation. Oh, this one was definitely one of the ones I kind of made for myself. So mechanical circuit system equivalence. So if you can remember the mechanical equations, maybe you can remember the circuit ones if you can remember the equivalences. So basically, for a mechanical system, you have x for a circuit, you have q, so position and charge, and then x dot and I, so that's velocity and current, and then m and l, so that's mass and inductance, b and r, and that's resistance, like air drag, I think is the B. I don't even remember it. Sorry. And then R is resistance. And then 1 over K and C, where K is your spring constant and C is capacitance. And then F and V, which is force and voltage. So I don't know if that one is helpful to other people, but it helped me. Centripetal acceleration. AC equals V squared over R. Hamilton's equations. P dot equals the negative partial derivative of H with respect to Q, and Q dot equals the partial derivative of H with respect to B. These are very important, and I never remember them. The effective potential function. This is V of R equals L squared over 2m R squared plus U of R. I honestly don't even remember what this is. I'm sorry. I apologize. Torque. So this is tau equals R cross F, where R is position and F is the force. Some of these are easier than others. The angle of repose. So this is mu sub s equals tangent of theta max. So this mu sub s is the static coefficient of friction, and then theta max is the angle of repose. It's the largest angle that you can incline it until it will start to move and overcome friction. The total energy of an orbit. This is E equals T plus V, where V is your potential and T is your kinetic. So it equals 1/2 m r dot squared plus L squared over 2m r squared plus U of R. So this is the effective potential and then the kinetic energy. The momentum conjugate to phi for angular momentum. This is L equals m r squared phi dot, which phi dot would be the time derivative of phi. The energy dissipated by friction is delta E thermal equals F times delta S. The Hamiltonian. H of P and Q equals the summation of P sub I Q sub I dot minus L, and H equals T plus U if U does not depend explicitly on velocities or time. So these would be energies. So as long as the potential energy doesn't explicitly depend on the velocity or time, then you can express the Hamiltonian that way. And then these are P and Q are the Hamiltonian variables. Angular frequency for a free oscillation. Omega equals the square root of K over M. Static, kinetic, and rolling friction. So you have static friction equals mu sub s times the normal force, and that's a maximum. Kinetic friction equals mu sub k times the normal force. And then rolling friction equals mu sub r times the normal force, where the mu's are the coefficients of friction. And the reason that I say this is a max is because it's just however much force it needs to oppose movement until the max is reached. All right, the moment of inertia. This is I, and it's equal to the integral of r squared dm. Spring constants combination. So this is saying if you have multiple springs, how do they combine? If they're in series, then 1 over the k equivalent is equal to the sum of 1 over k of the individual springs. And if they're in parallel, then the equivalent k is just equal to the sum of the individual k's. The work kinetic energy theorem. Pretty simple. This is just saying that the total work is equal to the change in kinetic energy. Rotational kinetic energy, K equals 1/2 I omega squared, where omega here is the angular velocity, and I is the moment of inertia. Work, W equals the integral from S1, S2 of F dot ds. So it's the integral of force dot displacement. The quotient rule for differentiation, F over G prime equals F prime times G minus G prime times F all over G squared. When I was in high school, we would remember this by saying low d high minus high d low all over low squared. I don't know if that's helpful for people. Terminal speed. So V sub t is equal to mg over b to the 1 over n, where drag is described by b times v to the n, where v is velocity and g is acceleration from gravity. The allowed energy levels of an oscillator, E sub n equals n plus 1/2 times hf. The angular momentum of a system about the symmetry axis, L equals I omega, where I is the moment of inertia and omega is again the angular velocity as a vector. Velocity as a function of time for a constant acceleration is given by V equals V naught plus AT. Kepler's first law is that planets move in elliptical orbits with one focus at the sun. The gravitational force between two masses, F sub g, is equal to g m1 m2 over r12 squared in the r12 hat direction. So this is Newton's very famous law of gravity, and g is the gravitational constant. Hooke's law is that force in the x direction equals negative k times delta x. So this is a restoring force from, say, a spring. The conservation of mechanical energy. So this is just a statement that the initial mechanical energy equals the final mechanical energy, as long as the total work done by all external forces and all internal non-conservative forces is 0. So if there's no work done, external forces or internal non-conservative forces, then your mechanical energy will not change. Newton's second law for angular motion. So this is saying that the net external torque is equal to the time derivative of the system's angular momentum. So this is somewhat analogous to F equals ma, which we might get to eventually. Newton's second law for a system says that the net external force on the system is equal to the total mass of the system times the acceleration of the center of mass. So again, this is another iteration of F equals ma, but just saying for a system. Velocity as a function of x given a constant acceleration. V squared equals V initial squared plus 2a delta x. cross product. So cross product says that vector A cross vector B equals the magnitude of A times the magnitude of B times sine phi in the n hat direction, where phi is the angle between them and the n hat direction is the direction perpendicular to both vectors. Or this is how I always learned it. The direction of the first, the direction of the second, and your thumb tells you the new direction. The parallel axis theorem states that the moment of inertia equals the moment of inertia of the center of mass plus mh squared for a parallel axis. The resonant frequency of a driven oscillator, so that's omega r, and that equals the square root of omega 0 squared minus 2 beta squared, where omega 0 squared would be the natural frequency. Pendulum equation of motion. So this says that the second time derivative of theta equals negative g over L times sine theta. And for a small displacement, you can approximate that as the second time derivative of x equals negative g over L times x, and omega equals the square root of g over L, so omega would be the frequency. Integration by parts. This says that the integral of u dv equals uv minus the integral of v du. I don't have any fancy mnemonics for this one, but it's funny how much this one has stuck in my head. This is one of the few that I have not forgotten. I've forgotten a lot of these. The Lagrangian of a system is a system of equations that is a function of q, q dot, and t, and it's equal to t minus u, where t is the kinetic and u is the potential energy. The potential energy of a spring is u equals 1/2 kx squared. The law of conservation of energy says that the change in energy of a system has to be equal to the energy in minus the energy out. Some of these are somewhat obvious statements. The gravitational potential energy, U, equals U naught, so the initial U, plus mgy. So you have to have a reference for this. The work energy theorem states that the external work on a system is equal to the change in the energy of that system, which is equal to the change of the mechanical energy plus the change of thermal energy plus the change of the chemical energy plus the change of any other energies. So that's somewhat self-explanatory. This is true if the external work is the only method of heat transfer with the system. Position as a function of time given constant acceleration. X equals x naught plus v naught t plus 1/2 at squared. The dot product. So the dot product says that vector A dot vector B equals magnitude of A times magnitude of B times cosine theta, where theta is the angle between them. And can also be written in Cartesian coordinates, A dot B equals A sub x times B sub x plus A sub y times B sub y plus A sub z times B sub z. So you can multiply the individual components by each other and sum them, and that is also equal to the dot product. Simple harmonic motion. What I was looking for here was the position equation, which is x equals a cosine omega t plus delta. So this is just a generic cosine with an amplitude, a frequency, an angular frequency, and a phase shift. Amplitude proportionality for a driven oscillator with no damping says that d is proportional to 1 over omega naught squared minus omega squared. So that's the natural frequency. Omega naught is the natural frequency, and omega squared is the derivative frequency. The chain rule for differentiation. So if you have function h that is equal to function f that's a function of the function of g of x. It's difficult to say in words. It's a very easy equation. Then basically the derivative of h with respect to x is equal to the derivative of h with respect to g times the derivative of g with respect to x. Sorry. Reduced mass for relative motion. So this is mu, and it's equal to m1 times m2 divided by m1 plus m2. Kinetic energy, 1/2 mv squared. It's always a good one. The damping parameter. This parameter is beta, and it's equal to b over 2m. The angular momentum of a particle. Here I was looking for a very generic equation, so L equals r cross p, where p is the linear momentum. Work by a variable force. W equals the integral from x1 to x2 of f sub x dx. And then the area under f of x versus x. Same thing. That's what an integral is. I don't know why I wrote that. The momentum conjugate. I always had trouble with this one. I don't know why. This is the partial derivative of L with respect to q dot. So L is the Lagrangian. And then this is conserved if the partial derivative of L with respect to q is 0. So if its corresponding q dot is conserved if q not dot is 0, the partial derivatives. The product rule for differentiation. So if you have three functions of x, h, f, and g, where h equals f times g, then the derivative of h equals the derivative of f times g plus f times the derivative of g. So that was it for my classical mechanics note cards. I know some of those are probably very specific things that I was having trouble remembering, and I needed to come up with a way to remember them, but I hope it was somewhat helpful for you, getting quizzed and having to think about these things. And if you found this helpful, feel free to check out the other subjects that I've also done note cards for. Well, thank you so much for watching, and good luck on your exam. I'll see you again soon. Bye.